Hi folks, thanks to be here for this talk about a guided tour of caching patterns. I am Nicolas Frankel. I've been a developer for now 2 decades. I also recently became a developer advocate. In the past, I also have been a lecturer at universities and higher education organization. So if sometimes this talk feels a bit like a lecture, it's probably because of this. Also because a guided tour, it lends itself to being a lecture. I work for a company called Hazelcast. Though this talk won't be about Hazelcast, I will be using it to highlight what I'm showing. Hazelcast has actually 2 big features. The first one, it's an in-memory data grid, meaning you can store data in memory and it's distributed by nature. And the other feature is in-memory data streaming. So you can transform your data, you can enrich your data, combine your data, whatever. Anyway, if you remember one thing from this talk is caching is a trade-off. You might have heard previously that caching is a sign of a badly designed system, that you should shy away from caching, that it's not true. Yeah, of course, sometimes you implement caching because your system is badly designed, but it is as it is, and you must cope with it in the most straightforward way. You cannot redesign every system every time. Now, regarding this trade-off, you have 2 actually trade-offs to make. So in 2 contexts is caching a good idea. You accept that you will have stale data because you want fast data, or you accept that you will have data, stale, because otherwise there is no data at all. And I always use the same example of an e-commerce application. E-commerce application that is designed around microservices. So you would have a catalog microservice, you would have a cart microservice, you would have a payment microservice, a checkout microservice, a pricing microservice. So the customer, they put items into their cart from the catalog, and at some point they go to checkout. During checkout, you will call the pricing microservice again. And because it's a microservice architecture and because it's distributed by essence, there is a possibility that at this point, it takes too long to get the price. And customers or potential customers, they don't like to wait. So they will leave the shop, they won't buy. That is bad. So in that case, it's better to cache the prices of the most used items in the checkout microservice. And if the pricing microservice returns, that's perfectly fine. Then we can cache the price. But if it takes too long, we just go into timeout very fast and we get the price from the cache. And of course, the data won't be exactly the correct data. But from a business point of view, it's better to sell at a slightly outdated price than not to sell at all. And of course, it can get even worse. The microservice, the pricing microservice might not be only slow, it might be down completely. So in that case, it's not about waiting, it's about returning anything. And again, a cache can help us. So remember, the point of view of the business, especially in that use case, is it's better to return slightly wrong data than not return anything at all. Business is happy. I have an application and I just want to cache some stuff. And the easiest way is your application will be the orchestrator. So the application will first get the value from the cache. And if the value is null, meaning there is nothing in the cache, or there might have been value in the past, but it had been invalidated. Anyway, right now, the cache is empty for this value. Then we will get to the data store. And in general, the data store is the database, but it can be anything. And then you get the value from the data store. And if you find it, because there is a chance you don't find it, then you put it in the cache. And then you return it to the client. And the next step is now the client gets the same entry from the cache, and it's here, and it returns immediately without going to the data store. So let's check how it's done. So here I've created a simple Flask application. I have couple of routes. The first route gets all entities from the database. The second route gets one by its PK, by primary key. And I also have a third route that allows me to put entities into the database. I mean, it's a simple CRUD application. I will be handling person, and before I start the application, what I will be doing, I will be populating my database with dummy data if the database is not already populated. I'm using SQL Alchemy, and I'm using SQLite to put the data. Of course, it's not how you would do it in production, but it's for simple demo. So let's start it and let's see how it works. So I can curl local host 5000, and I will get all entities here, and you can see that they correspond exactly to what I created because it's a brand new database. Or I can ask for one PK, or I can try to put some data into it. So curl post local host 5000, and now I must remember the syntax. It's header and it's content type application JSON, and I will pass in this following data. And now if I curl again for everything, I will get this new entity. I don't need HTTP, localhost 5000. Yes, and now I have this new entity that is created. So I'm very happy. I have an application that works, but for whatever reason, it's too slow, and I want to implement caching. So I go to my faithful IDE, and here I already created everything because, I mean, it's too dangerous. So I will be using Hazelcast, as I mentioned, and the only thing that I'm doing, I will create a Hazelcast client, and from this client, I will get a dedicated map. By default, we have a non-blocking behavior, but here I want to have it as simple as possible. So I will create a blocking cache. So every time I put stuff into the cache, I can directly get the result. And this is how it works. When I get all, for every person that I got, I put it into the cache. I write it down into the log just to be sure. And when I get one, I will get the PK. I will check if the cache contains the PK, and if it contains it, I return it from the cache. Otherwise, as I mentioned, I will write it down into the cache and return the person directly. So let's see how it works. So here I will first start my cache. Hazelcast start. So I already installed it. Again, it's not about showing you Hazelcast. It's just imagine that I have a cache running. It's a distributed one. And now I can start the application. And I can curl it. So curl localhost 5000, get the first entity, and it returns me Joe Dalton. And at this point, I should have like person with PK1 not found in the cache, person with PK1 set in cache. If I ask it again, the same key, then I have PK1 found in cache, so I don't go to the database. And of course, I can curl everything. So now every entity is in the cache, and if I ask for a new one, then all entities are in the cache because I've set them all, and now a PK1 has to be found in the cache, so you don't go to the database again. That's actually the cache aside. And of course, it's only about reading, but we can also do the same for writing. And this is actually even simpler. So every time you write in the database and you check that it works, of course, then afterwards you can set in the cache. And in the code, it's the following translation. Like, we commit, and at this point, if there is no error, we can set the key in the cache. So here we will create a new entity again. and I just want to create Jake do, for example, because John has already been created. Okay, and now I want to curl everything, local hosts 5000. We can see Jack, and it's in the cache. Perfect. That seems easy enough. And actually, you don't need any real caching provider for that. And any hash map will do in that case, even though you need a limit, you need an invalidation strategy, whatever. It's straightforward. This is in general what people think about when they are using cache. But the cache can be so much more. So that's the first pattern, is cache aside for read and write. The second pattern is actually read through. And with read through, you actually are not orchestrating. Your application is not orchestrating. What you are doing is you are only interacting with the cache itself, and the cache is configured to talk to the database. So on one side, it might be beneficial because you actually only talk to the facade of the cache. On the other side, you need to configure the cache accordingly. You need to be sure that the cache works according to your needs. Let's see how it works in the code. So for convenience purpose, I've created a new project with the cache itself because it will allow me to do some changes. And in that case, the change is the following. So normally you would just use again the cache, and you would write the code, and then you won't care about it, because I think that's important for you to know. Right now I've created a new project. In that case, it's a Java project, but the idea, even if you are a Python developer, is quite straightforward. The idea is we have this stuff called SQL map loader, and basically what it does is when we are calling this load, and we won't be calling it explicitly, it will be handled by the caching provider itself. It will look into the database. And of course, there is a load all, and of course, afterwards, there is a load of key. There are a lot of methods that you need to implement. Well, not that many, actually. If we look, there is this load all keys. And of course, there is some initialization stuff. Because here I want to say, hey, I want to read from this database. But once that it's done, we should forget about it. We can just run the cache, and we will have this application. But as you can see on the routes, we are not interacting with, sorry, not here. Of course, here we are still interacting. Here, we are not interacting with the DB anymore. So we moved the code that interacted with the DB from the application to the cache. So now that our application is actually much simpler. And what we do is just, read from the cache, and the cache will be the one to say, oh, it's not in this cache, so I need to load it from the DB. It will retrieve it from the DB, put it in the cache, and return it to the application. The application, in turn, will just, get it. Likewise, you can do the same for the PK. So let's see how it works. I can now call the application, localhost 500/1, and I get directly the entity. If we check from the Python application, of course, there is no logging. We directly get the stuff. And on the caching provider side, we can see that, we have been loading some data already. We are eagerly loading. It's not necessary, but we are eagerly loading. On the sides of the writing, we are still interacting with the database because we are only doing read through. We are not doing write through. So the next step is, so let's see write through. And again, it's the same as before. We are interacting only with the cache, and the cache itself interacts with the data store. So let's simplify our code using write through. That requires the next step. And in that case, now this map store, this class, implements a new interface, which is called map loader. Again, this is Java code. I don't want to go into the detail, but it adds a couple of additional methods. actually store all, and also, yeah, I'm too lazy to implement this now, but, and then you can also do the delete stuff and the delete all stuff. So let's start the cache with that in mind. Okay, so we can still curl, everything is fine. We can still curl everything is still fine. And now we can post, and post will be doing right through. So curl, I will be doing that because I'm lazy. Okay, and I had John, I had Jack, now I will have like Jane do. And here I have an issue. I don't get the ID of the entity because now I've migrated my store logic to the cache. So here I need to provide the ID, which can be an issue in some cases, but here, let's suppose it's not. I will be using ID 10. Now it works. And of course, we curl ID 10. It's already in the cache, because again, we are only interacting with the cache right now. That's pretty good. So far, I'm quite happy. Notice, however, that in that case, what we are doing is every time we are waiting until we get confirmation. So here, this is, if you remember your UML lessons, this is synchronous. So we put data into the cache puts data in the data store, and we wait until the data store has done its job, and we get the response, and we return the response. And it might be good, depending on your use case, it might be not so good. We are not that fast as we could. So the next step is, once you have implemented right through, to say, hey, but perhaps we could be much, much faster. How much faster can we get? Well, it's easy. When you put stuff into the cache, you just return immediately. And you leave it up to the cache to put the data in the data store. And again, it has benefits and it has disadvantages. Benefit, of course, I mentioned it. It's like super fast. You are only interacting with the cache and you return immediately. Problems, that you are not guaranteed that actually this will happen. There might be some issue with the caching provider, it might go down. There might be some issue with the data store, it might go down. So you might have wrong value in the cache, and the client thinks that everything has been done in the right way. So this is eventual consistency, and sometimes it might not be consistent at all, but you are fast. And again, it's not bad per se, but there are some use cases where you value speed over consistency. It's up to you to decide, but this is right behind. So you are just saying, okay, I will do everything asynchronously. Let's see how it works. So here we go to right behind, and actually the only thing that we need to change is how we configure. In that case, that's very Hazelcast specific. We just need to change a single line of configuration. We just said that there is a write delay seconds. So between the time that you actually do a change and the time that the change gets triggered to the data store, there is 20 seconds. And the good thing is that during that time, there might be other requests coming in for the same entity. So there will be only one call to the data store, the latest one. Again, pros and cons everywhere. The next pattern that I want to show you is refresh ahead. One of the problems of the cache that I mentioned is you've got stale data. In order to cope with stale data, we are doing cache invalidation. So when you put an entry into the cache, you set it's valid for a specific amount of time, let's say 5 minutes. Afterwards, that gets cleared, and next time your client gets the entity, the entry, it's not here, so we need to fetch it from the database. And at that point, we need to do the whole flow, and it takes time. So you will probably have long requests that need to access the database, and slow requests that need to access the database, and fast requests when you hit the cache. That's not a necessity. What you can do, again, with some caching providers, is that when an entry is close to invalidation, then there will be an eagerly fetch from the data store. So again, that is asynchronous. Your client doesn't know anything about it, but once you've put an entry into the cache, it will be refreshed automatically when it's close to expiration. So if you set the invalidation period to 5 minutes, like when it's close to 5 minutes, we'll fetch the data from the data store, so that you know that every time the entry will be like, we'll have the latest stuff from the latest 5 minutes, but more importantly, the client will fetch the data always from the cache. And of course, the problem in that case is that your cache will always be full. So once you've put an entry into the cache, it will stay there forever. You can only grow because you never invalidate anything. When you invalidate, you put it again. That's pretty good if you accept this trade-off. But that means still that the first request will still be slow, because the first request there will be no entry at all, and you will need to fetch from the data store. Now imagine that we will pre-populate the cache with everything. That could be a pretty neat idea. Again, if you've got like a lot of storage, if memory is not an issue, we could pre-populate cache. We need to update it. And again, refresh ahead is a good idea. But if we set the time to live of 5 minutes, that means that there is a time span in which, a time window in which the data won't be valid. So when you start thinking in frames, in windows of time, and you have an issue with that, probably that's not the right way to address the situation. In that case, if you really want to have like the window of inconsistency between the cache and the data store to be as small as possible, you should be event driven. You should be, every time there is a change in the data store, it can be reflected in the cache. That's another level of complexity, but it works. But for that, we need an additional property. We need to have streaming. So we will have streaming that gets the changes from the data store, and every time there is a change, it will set the value in the cache. And on the application side, not only we will interact only with the cache, but the cache itself won't fetch the data from the data store. So everything has been like moved to another component. Now it's this streaming pipeline's job to get the data from the data store and into the cache. So it's another level of architecture complexity for another level of benefits. Let's see how it works. Now, the cache itself is not necessary anymore because, as I mentioned, the cache itself doesn't interact directly with the database. So we can remove this one. There is no like SQL map store. What we have created on the opposite is a cache head stuff. So again, this is Java code. I don't want to delve into the specifics, but we've created a pipeline. And even if you are not a Java developer, you can read from MySQL, and I will map. So here I have an object called change record, and then I will I will transform the change record to a map, and I will transform the map to a JSON. And from this JSON, I will extract the ID, which will be the key, and put this entry in the cache. And well, the rest is not super interesting. Basically, it's just like configuration to say, hey, where do we get the data from? So here I'm using MySQL because SQLite is not made for that. So here it's the host, it's the login, it's the password, blah, blah, blah. And here we are just configuring where we will write to. So it's a remote cache. For that, I've created a Docker Compose file. So here you can see, here I have my cache, very simple cache. Again, I'm using Hazelcast, you can use anything you want. Here I have my application that I have Dockerized, and here I have the pipeline, and everything has been Dockerized. And of course, I have the database. So let's start this. I'm ready. I can start playing with my application. So here everything is Dockerized. I don't need to start it in the IDE. I can directly like curl. Let's do that. So let's say curl localhost 5000/1. Good, I got it. And you can see it's like, I wouldn't say blazingly fast because I don't like this term, but very, very fast. And let's say here I want 2. And as you can see, again, it's very, very fast. If I get everything, it's very fast. I have an issue with the formatting. And then the last stuff I want to post. So let's post something, H. And here I'm on a new application, so I can put everything like this. And if I curl localhost 5010, it's already in the cache. In this talk, I've shown you several patterns to interact with your cache. The first one, as all developers do, is the cache aside. The cache aside, you don't care about the capabilities of your caching provider. Your application is the orchestrator, and then you go to the data store and you go to the cache to read and write. And it's your application's responsibility. Once you get comfortable with your caching provider, in general, you will use read through and write through because it removes the responsibility of this orchestration flow from the application. Your application doesn't care about the cache. It should just like use one data store, and in that case, the data store can be seen as the cache. At some point, you might be faced with performance issues you are blocking. If you don't have solid consistency needs, then probably you will need to check write behind. With write behind, when you are hammered by several requests on the same entry, what you do is you defer the write asynchronously, and then you will only write the last one, which makes your system much more resilient. If you value the fact that your application is fast, you might know that every time that the cache is called, you will need to go to the data store. In that case, you might say, hey, once I've requested an entry has been put into the cache, there might be slow pass, so when this entry has been invalidated. So one idea is, once an entry has been put into the cache, when it's nearing invalidation time, you will refresh it asynchronously. And in that case, once an entry has been put into the cache, there will be only fast requests because you will be always hitting the cache. It will be a hot cache. That, of course, means that you will have memory available. The problem is it doesn't handle new data. Now, if you got a lot of memory and you want this window of desynchronization between the cache and the data store to be as small as possible, you can have cache ahead. And in that case, you remove everything from your application and you remove every logic from the cache itself. And you are just creating a new pipeline that will read the changes directly from the database and put them into the cache, so that your application actually will consider the cache as the data store, and you know that this cache is very, very closely in sync with the data store. It's not completely consistent because we are talking about distributed systems, so it can never be consistent as you would think about ACID, but the window of inconsistency is as small as possible.